Hey guys, Mrs. Traver here. We're going to work through our beginning of chapter 6, which is all about systems of equations. We've got 3 different methods that we're going to cover in this chapter, the first of which is graphing method. So before we get started on graphing method, though, let's talk about what systems of equations actually mean. So the game plan when we're thinking about these is that we're trying to answer the question of where do two functions intersect? And we just got done with chapter 5, which was all about lines and linear equations. So we're going to be mainly concerned with the linear equations aspect of it. So what I'm really talking about is where do two lines intersect. So the most common is that they intersect in one spot. So one goes here and one goes here, and they have one spot where they cross. This is the situation where we have one solution, and that solution is in the form x, y. The next situation is maybe they never cross. That picture would look like a parallel line set. So if they have no solutions, and that was because they were parallel. And the last type to consider is that where there's, let me draw it like this. There's this line, and then there's this other different line that is also right here. I draw them a little bit bold. But it's a situation where we have two lines that are on top of each other, or you can think of it just as being the same line. So these lines intersect at every single point available. So that would be an infinitely many situation. Infinitely many solutions. An example of what this would look like when solving is like, say we had 4 equals 2. That's false. So no solution of x or y would ever make 4 equal 2. Infinitely many solutions is the kind that could look something like -7 equals -7. That is true for every x and y. So those are the 3 type of answers we'll have: one solution, no solutions, or infinitely many solutions. We're going to work through a few examples today, and we'll see some of each of these in those. So let's get our first example going. All right, so here's our first example we're going to run through. We've got 2 equations of lines here, y equals 2x minus 4 and y equals -2/3 x plus 4. I've got them in 2 different colors because I'm going to graph them in these 2 colors. I think that'll help us out a little bit to see which one's which when we graph. So notice they're both in slope-intercept form. Like I said, we just finished chapter 5, so I am assuming you're coming into this section already knowing how to graph lines. So this is not the video to be watching. If you need help on knowing how to get from here to the graph, you need to go back and look at a previous video in order to know how to graph from slope-intercept form. So here's a quick review of it. You should be starting at your y-intercept at -4, and then using your slope to rise over run. It's important, especially in graphing method, that you extend the line out as far as you can. So with a slope of 2, instead of just doing the very first point and connecting those 2 dots and calling it good, we need to extend this line out as far as we can to the edges of our coordinate plane. So I'm going to keep doing my slope until I run out of graph space. And that'll give me a best approximate, a best answer that I can get. So there's my first line. My second one is going to be starting at +4, down to right 3, down to right 3. So here's my second guy. And you can see, because that I extended out, I have the intersection right there bolted already. My answer on this guy was this point, and I'll bold it in even further. Our answer is the point. So that is the point 3, 2. I'll put it right here. So there's our solution. We had one solution, and it was at the point 3, 2. Let's look at another. All right, let's look at this example. I've got y equals 1/2 x plus 4. That's in slope-intercept form, so let's go ahead and start to graph that. We're starting at +4, and we've got a slope of rise 1, run 2, or I could drop 1 and go left 2 as well. So I'm going to do that so I could extend it out. My second guy is not in slope-intercept form, it's in standard form. You could rewrite this and solve for y, or what I would do is find the two intercepts in order to graph those guys, but I think that they would be fractions. So let's actually take this guy and rewrite it. So let's rewrite it as 2y equals, let's subtract 5x to the other side, so negative 5x plus 8. And then let's divide everything by 2. I've now got y equals negative 5 halves x plus 4. And now we're in slope-intercept form. We can go ahead and graph that. So we're starting at positive 4. Oh, I already found our intersection there. Let's graph our line to keep complete. Drop 5, run 2. And I can't even graph that one more time. So we found that they both have the same intercept at 0, 4. So there is our one solution. Let's run through another. All right, let's check this guy out. They are both in this one in standard form. So if we can in standard form, it's easiest to graph by using the intercepts. Whoa, there we go. So let's do that. Our x-intercept is when y is 0, so that would get covered up. X equals negative 9. That is far off my graph, so I'm not really care to use that point. Let's look for our y-intercept. That would be when x is 0, so that would be y equals 3. So at least I've got that to start with. And then if I can get my slope, then I can graph the next point. So let's rewrite this guy. I've got, let's subtract our our x to the other side. So negative 3y equals negative x minus 9. And then divide everything by negative 3. So y equals 1/3 x plus 3. All right, so there's our slope. I can use that. Again, extending my line off the as far as I can on the coordinate plane. My next guy, let's see, my x-intercept is when y is 0, so cover that up. We've got an x-intercept at 6, so that'd be right here off my graph a little bit. And then my y-intercept is when x is 0, so that'd be at negative 2. Now these two look like they are parallel to me, but we should check by thinking about the slope of this guy. So this one had a slope of 1/3. Let's check our slope of our blue line to make sure that that's also 1/3, because looking at my graphs, I'm kind of assuming that that's the case. But we do have to be a little bit careful, because sometimes, for example, say I had a coordinate plane and I had this line and this line. Now technically those don't cross yet. Like they don't cross on the coordinate plane, but I know if I were to keep going that they are going to cross. It's just off my chart. So I want to make sure that that's not the case here. I'm pretty sure looking at these, we graphed them really nice, that these are going to be parallel lines. But let's be sure of that by looking at the slope of the blue one as well. So let's take this blue guy. Excuse all my arrows. I hope that's not confusing. And let's solve for it. So let's subtract the 2x to the other side. I'd have negative 6x equals negative 2x plus 12. And dividing everything by negative 6. Oops, that's supposed to be a y. I'd have y equals 1/3 x minus 2. And check it out. We do have the same slope. So this is a situation where we have no solution. And we know that because these are parallel. All right, let's do one more and we'll call it a day. All right, so our very last one here, we've got y equals 5 halves x. 5 halves x minus 4. That's in slope-intercept form, so I can go ahead and graph my b first. And then use my slope, rise 5, run 2. It'd be nice if I had a ruler for this, but I don't. If you do, that'll make it even nicer. My next guy, again, it's not in slope-intercept form, so I can move it around to make it be in slope-intercept form. Let's go ahead and do that. Actually, I think this is the same equation as we did above. It is. This is the same one we just did right here. And we solved it to be y equals negative 5 halves x plus 4. All right, so if we just reuse that line, notice my first line I already graphed was negative 5 halves x plus 4, and then this one, when I rewrite it, it's the same line. So if I was going to graph this one, I would graph it right on top of the other one. So because these are literally the same line, just written different ways, we have a situation where we have infinitely many solutions. And that's because they are the same line. All right, so we've ran through 4 examples, one of each different type, a couple of the 1 point. So taking a step back and looking at them all together, we've got the situations where you have one solution on these guys, and then one where there's parallel lines on this one, and where we have the same line in example 4. The next ones that you're going to see, this is graphing method. The next 2 that you're going to see is substitution and also elimination, which is also called linear combination. So you'll run through these 2 examples in the next sections in 6.2 and 6.3. I will see you guys next time.